Every time you see a colorful Doppler rain map showing rain sweeping across your region, there's an invisible system at work, sending invisible energy pulses through the sky. But how does radar actually see weather? And what's next for the future of forecasting? Today we're diving into microwave radar, the physics, the technology, and why the phased array radar system could soon replace the current Doppler system we've used for decades. I'm Ben. This is Physics or Bust. Last week, the National Severe Storms Laboratory released updates on its phased array radar demonstration project. They've been running test operations using SPY-1-derived radar panels, and for those of you that haven't heard of that, that's the same tech that the Navy uses. And early results show that the phased array radar, or PAR system, can scan the atmosphere 5 times faster than the current Doppler system. Faster scans means faster warnings for things like tornadoes, flash floods, and rapidly developing storms. This is part of a broader push to replace the current NEXRAD Doppler network, which, while reliable right now, is reaching the limits of its design. So how does radar actually see a storm? The answer lies in microwaves. No, I'm not talking about the microwaves on your kitchen counter, although they do use a similar EM range. We'll dig into the physics in a minute, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. Radar systems emit short bursts of microwave radiation, typically in the S-band, which is from 2 to 4 gigahertz, or the C-band, which is from 4 to 8 gigahertz. These waves travel outward from the radar dome, and when they encounter things like raindrops, hail, or even bugs, a portion of the wave scatters back to the radar. This returning echo is then analyzed for a few pieces of information. Time delay from when the wave left the radar system to when it returned, in order to determine the distance that the object is away from the radar system. Signal strength of the wave that returns back lets the system know what size and type of object reflected the wave. And it's analyzed for the Doppler shift, which tells us how fast the object is moving relative to the radar. That's how we can see wind patterns inside thunderstorms, including rotating updrafts that may become tornadoes. So why change the system now? One major difference between the NEXRAD system and the PAR system is that a PAR system does not rotate mechanically. Instead, it uses electronically controlled beam steering to scan different parts of the sky within milliseconds. This means that PAR can continuously monitor storms in 3D by looking at different altitudes of the storm cell and scan multiple targets simultaneously. It's like upgrading from a rotating security camera to a network of ultra-fast laser pointers that can track everything at once. One other huge advantage is that the PAR system can handle both weather and aircraft tracking simultaneously. This is a huge deal for the FAA and the NOAA because they're looking to save money on this next upgrade to the radar system by having one radar system for both air traffic control and weather forecasting. Now let's dive into the physics behind microwave radar systems. The radar's ability to detect an object depends heavily on the wavelength being used being comparable to the object's size. Raindrops, which are typically 0.5 to 5 millimeters, scatter microwaves efficiently when the radar system uses a wavelength of comparable size, typically from 5 to 15 millimeters. This is called Rayleigh scattering, where the object is smaller than the wavelength being scattered. However, if the drops get too small or the frequency is too high, signal strength weakens. This is why K-band radar, which is high frequency and small wavelength, is better for detecting drizzle and cloud droplets, while S-band is better for heavy storms. Also, radar range resolution depends on pulse length. Short pulse equals greater resolution. And the PAR system, even with updating about 5 times faster than the current NEXRAD system, keeps up with the resolution, so we won't be seeing any drop in quality when we change from the NEXRAD system to the PAR system. And here's something few people talk about. What happens when 2 radar systems are operating in the same area and their beams overlap? Shout out to viewer Pickin' Cotton for posting this comment in a previous video. I would be extremely interested in understanding the physics of OmniRad microwave weather radar stations and the implications of crossing beams with other OmniRads. With OmniRad being short for omnidirectional radar, PAR is a type of OmniRad. So when two radar systems are operating close enough together and their beams do overlap, this is called co-channel interference. And it can cause ghost echoes, signal dropouts, and radar anomalies like double returns or noisy precipitation artifacts, making it look like there's rain where there really isn't anything. This happens because the microwaves are energy waves, and just like sound waves, where you can create loud spots with constructive interference and dead spots with destructive interference. Microwaves from two different stations can also have constructive and destructive interference when they cross each other. In tightly packed radar networks, like military operations, airport radar, or storm chasing teams using mobile systems, coordination is crucial. The NEXRAD system had more trouble with this kind of problem than the PAR system will because the NEXRAD system had rotating antennae, and if their rotations got a little bit off so that they were hitting each other, it would take some time to make the adjustments to make sure that the two stations would be scanning the overlapping area at different times. Modern phased array radar will remove this problem almost completely with the right interconnectivity, because they can not only use frequency agility to make sure that they're not using the same frequency as the second station, but since the direction of their beam is controlled electronically instead of mechanically, they can adapt in real time and just scan a different area of the sky and come back to it after the second station's done. All this radar physics isn't just academic. The decreased scan time will mean faster and more accurate tornado warnings, and we'll be gathering more data than ever before with the PAR system, so the weather forecasting should increase in accuracy. We may even detect climate shifts in real time. The future of forecasting is tied to how well we can sense, track, and understand the atmosphere in motion. And that future is being built right now, with microwaves, math, and some really brilliant engineering. Would you trust a fully AI-driven weather radar system? Let me know in the comments below. For more updates on space and technology, make sure to like and subscribe, and remember, keep asking questions. I'll see you on the next video.